Welcome to our next lesson. 8.2 covers similarity transformations. We learned previously about dilations, which was a transformation that either reduced the size of an object or enlarged it. Now, it's considered non-rigid because it preserves shape and not size, and we could see that because the shape or the size was either increased or it was decreased. Rigid motion transformations are those transformations that you guys learned last year in Math 1, and for some examples of the rigid motion transformations are reflections, translations, and rotations. And they're considered rigid motion because it preserves shape and size. Now, this lesson we're going to be doing some similarity transformations, and similarity transformations may be a dilation or a combination of a dilation and other rigid motions. Now, two geometric figures are considered similar if and only if there is a similarity transformation that maps one of the figures onto the other. They have the same shape, but not necessarily the same size. So later in example 2, we're going to be describing those similarity transformations. Don't worry too much about that right now. That's just vocab. Now, we're going to get started on example 1. For example 1, we're going to be performing a similarity transformation. We're going to graph the figure and its image after the similarity transformation. So for these problems, you're going to be given some points, and then you're going to be given some transformations. So the order in which you do the transformations is the order in which it appears. So we'll first be doing a translation and a dilation. Now, if you don't recall the different types of transformations, don't worry, I'll post a resource for you to remember, but I'm pretty sure that once we get started doing these, it'll come back to you guys. So I'm going to start off by graphing ABC. I'm going to use 3 different colors for the 3 different steps that we need to take in order to perform these similarity transformations. I'm going to first start off by graphing ABC. There is ABC. We're first going to perform a translation. So we are moving each x coordinate over 4. So we're adding 4, so we're going to go to the right 4. And then we're going to add 1 to each y coordinate, so we're going to be translating each up 1. Right, so we can just count. So we can go right 4, up 1 for each of those points. There is our figure after a translation. I'm going to write down the coordinates so that we can perform the dilation mathematically. Or if you're great, then you can do it all in your head, but I'm just going to write down all the steps. Coordinates after the translation of 4 units to the right and 1 unit up. So I'm going to perform the dilation now. Notice that each x and y coordinate is multiplied by 2. So we're going to perform that algebraically, so multiply each x and y by 2. These are the points I got. Now, since the next transformation, the dilation, is a transformation of the one that comes before, I'm using 2 apostrophes. So this is A double prime, B double prime, C double prime, which has coordinates of 0, 0, 4, 6, and 4, 4. Now I'm just going to graph this, and we'll be finished. We have our first transformation. I'm going to do one more. For C, we have a line segment. It's composed of 2 points. And we're going to be rotating it 90 degrees about the origin, and then we're going to dilate it. I'm going to start off by graphing CD. Next, we are going to be doing the 90-degree rotation. Now, for 90-degree rotation, well, firstly, rotations we usually rotate counterclockwise. And we can use a rule for the rotation. So a 90-degree rotation will turn a point x and y. Basically, the x and y are going to switch, but then the y becomes negative. Okay, so if you're great at remembering rules, formulas, you can use this. Another way that you can do a rotation is you can just flip your paper, and then you can just make note of where the points are, pretend like the graph is upright, and then record the points that you get. So this would be at -2, 2, and -2, -2. So I'm going to graph those 2 points. Alright, so our point C prime will be at -2, -2, and our point D prime will be at -2, 2. Alright, lastly, we're going to do that dilation. Notice that we're taking half of both the x and y. So let's perform that algebraically. So I get that C double prime is at -1, -1. D double prime is at -1, 1. I'm going to graph these 2 points. All right, and there we go. We have our similarity transformation. All right, now for example 2, we will be given 2 polygons that are similar. And we will need to perform some transformations so that we can map the desired polygon onto the other. So for this first example, we want to map PQRS to WXYZ. So we want to describe transformations that will make them overlap, or make PQRS overlap with WXYZ. There's a few ways that you can do this. So you can either perform the dilation first, and then transform it so that it is in the right position, or you can do the reverse. That's usually my preference. I usually prefer to transform it so that it's in the right side of the graph, and then perform the dilation after. So that's what I'm going to do. So looking at PQRS and WXYZ, I noticed that they are reflections across the y-axis. So I'm going to first reflect PQRS so that it is on the other side of the axis. All right, so I've performed the reflection across the y-axis. Now let's figure out what the scale factor is. I noticed that this top part of the trapezoid has 1 unit long, and the upper part of this trapezoid is 3 units long. So the scale factor, we want to go from new divided by original. So we have a desired length of 1, and our current length is 3. So we are going to have a scale factor of 1/3. All right, so each of these points that we got, we want to multiply it by 1/3, and that's going to give us the desired trapezoid. All right, so I'm going to write down the coordinates for the reflection, and then we will scale it. All right, so I get these coordinates for the reflection. Now I'm going to dilate it with a factor of 1/3. So I get these very coordinates for the dilation: 2, 1, 1, 1, 0, -1, and 2, -1. We just need to check that that is correct for the trapezoid that we are concerned about. Notice that W has a coordinate of 2, 1, X is 1, 1, Y is at 0, -1, and Z is at 2, -1. So we've performed the correct transformations to go from PQRS to WXYZ. All right, so the steps to map trapezoid PQRS to trapezoid WXYZ is to reflect PQRS across the y-axis, then dilate by 1/3. All right, we're going to do this one more time. We are going to perform the similarity transformation that will map quadrilateral DEFG in blue to quadrilateral STUV in green. Straight off the bat, it doesn't look like there's a reflection that goes on. If it was a reflection, then it would be like a perfect mirror, but I don't see that. So I'm thinking that there might be a rotation that's going on. So I got to figure out how much we are rotating DEFG by to get it into the correct position STUV. Right? So I noticed that point F and point U, they correspond to each other. We can also see that in the naming of the quadrilaterals. So I'm going to rotate my paper until I see that point F is touching the negative side of the x-axis. That's going to tell me how much I need to rotate my figure by. So I'm going to rotate it once 90 degrees. F is on the positive side of the y-axis. So recall that when we are doing rotations, we have to read it as if we didn't turn the paper So this would be the y-axis and this would be the x-axis. So we're pretending that we're reading it right. So this isn't right because I wanted it on the touching the negative part of the x-axis. So I'm going to rotate one more time. So I've rotated my paper 180 degrees. Notice that F is now on the negative part of the x-axis, which is what I wanted. So since I turned my paper completely upside down, this is a rotation of 180 degrees. At this stage, you can record where these points are if we're reading it upright, or we can use the rule, and I'll write the rule in a second. Our first step is going to rotate by 180 degrees. Now, when you rotate 180 degrees, your coordinates, your original coordinates x and y, we're just going to take the negatives. It'll become negative x and negative y. Let's use that rule to rotate D, E, F, G 180 degrees. I get that the rotation will give me these points. I'm now going to graph these points. And now I have the quadrilateral D, E, F, G after a rotation of 180 degrees. Now we got to figure out what the how much it's being dilated by. Unlike the previous example where we had some straight lines that we can count the units for and calculate the scale factor that way, we don't have that over here because we have these diagonal lines. We can't count the units if our lines are diagonal. So another thing that we could do is we can compare points. So for example, our point G prime here is 0, -1. It should correspond with this point right here, V. Or we can use another one. Our point F prime here should correspond with our point U here. You can use any pair of points that you want, and you're just going to compare so that you can figure out what the scale factor is. So because I used F earlier, I'm going to use F here. So F prime should correspond with U. And I noticed that U is at -2, 0. All right, so how do we go from -4, 0 to -2, 0? Let me use another point just to compare. S seems to be a good point. So S corresponds with our point right here, G prime. And I noticed that S has coordinates of 1, -1.5. All right, so comparing, one thing you could do is you can divide the x and y coordinates, or if you notice right away that we are taking half. All right, so there's a dilation of 0.5. And we can make sure that this is true for all the other points. So E corresponds with T, and T is at -0.5, -2, and then lastly, our point V, this is at 0, -0.5. We just want to make sure that each of the x and y coordinates is exactly half, right? And I noticed that that is right, so our dilation of 0.5 makes sense. If you have any questions about this lesson, please ask me, and your homework is going to be posted onto Google Classroom. Stay safe out there. I miss you guys, and I'll see you next time.